Connected objects are a neat application of Newton's second law, and they've got some cool math to solve them once we get going. Generally speaking, some questions will have shortcuts that you might be able to get around less math to solve them, but connected objects, we can always solve them if we always kind of follow the standard method. If we draw a free body diagram for each object and set up F net equals ma for each object. Forces that are on a funny angle will need to get components if they show up. When we're working through F net equals ma, each object is going to have the same acceleration, nothing stretching or doing anything weird, so they're all moving kind of together. There's a neat connection with the connecting force. That connecting force that maybe is speeding one object up is slowing another object down. So you'll see as we work through the math that we get some neat kind of canceling out, makes the math actually a little bit easier to solve. I've made up one, we'll do it together here. A little bit complicated because it's got three objects and a force on a funny angle. I'll just make up numbers. Let's say that this first one has a mass of 1 kilogram. Second one, let's say 2 kilograms, and we'll follow the pattern. The third one will be 3 kilograms. Let's say that the coefficient of friction on this first one is 0.1. We'll just follow the pattern backwards. The coefficient on the second one will make 0.2, and the coefficient on the 1 kilogram, let's make 0.3. To pull this whole works, let's say that the applied force is 20. And we're going to put it on an angle, so we have to do a little bit of component work. Let's make that an angle of 30 degrees. It's up to you where you start. I always like to start with the one that I see as the easiest, and that's the last one. So in this case, I would start with the 1 kilogram. On the 1 kilogram, it is a rather rectangular free body diagram. We've got gravity pulling it down, normal fighting gravity, friction backwards, and a connecting string that's making it move forward. Since we're eventually going to have a second string, I'm going to call this FT1. So FT1 is a connection between the 1 kilogram and the 2 kilogram. I would call this the boring case when we consider the vertical component. There's nothing happening in the vertical, so the normal completely cancels out gravity. In this case, that's going to be mass times 9.8. It's got a mass of 1, so this is going to eventually be just plain old 9.8. In the horizontal, we'll set up F net equals ma. We've got a tug of war. The string is pulling it forward, that's our FT1. Friction's pulling it backwards, and that's equal to ma. I don't know what the tension is, just going to call that FT1. Friction is always mu times Fn, and that will be equal to ma. Plugging in what we know, FT1, take away the coefficient I made up for this one was 0.3. The normal force, we did that quick easy math to get 9.8, and that's equal to 1 times a. Cleaning that up one last step, FT1 minus 2.94, double check that on a calculator, equals a. That's as far as I can go. Oops. I don't know FT1 and I don't know a, so I'm stuck there. Let's call that equation 1. Now we're going to move on to the next object, the 2 kilogram object. I'm going to slide over here. Actually, let's see if we can, there we go. If I do that way, then we can kind of see it. On the 2 kilogram, a very similar free body diagram. Gravity down, normal up. A string is pulling it forward. This is a different string, so I'm going to call it FT2, the connecting force between the 2 and the 3. The force backwards is FT1, the string we just talked about, and there's some friction, so we actually have 2 backwards forces. In the vertical, it's a boring case again, nothing's happening. So normal force is equal to gravity. That's equal to m times g. In this case, because it's a 2 kilogram object, 2 times 9.8 is 19.6. Now, the more exciting horizontal component, when we set up F net equals ma. We've got one forward force, that's the string that we called ft2. We've got a backwards force from the other string, ft1, and we've got a backward force from friction. That's going to be equal to m times a. I don't know ft2, so that's going to stay as letters. I don't know ft1, that stays. The force of friction is the coefficient. For this one, that was 0.2, multiplied by the normal force. For this one, that was 19.6, and that's equal to 2 times a. When we clean that up, ft2 minus ft1 minus, when I clean up that number, 2 times 20, but we got a decimal place there, so we're going to be really close to 4. I'm getting 3.92, and that's equal to 2a. We're going to call that equation 2. Okay, one more to go. Let's go back to the diagram to refresh our memory. We're going to draw the free body diagram and set up the components for the 3 kilogram. The 3 kilogram has got the one rope attached to it, an applied force on an angle, and some friction. So, scrolling down here, on the 3 kilogram, when I draw the free body diagram, normal upward, gravity downward, 2 things backward, the string, this is one we called ft2, and friction, and we've got an applied force on an angle. The number I made up for the applied force was 20 newtons, and it was on a 30-degree angle. This one's not a boring case. We have a little bit of work to do to get the normal force. If I consider all the upward forces, they balance all the downward forces. In this case, I've got 2 upward forces, the normal force and the component of the F applied. It's opposite the angle, so it's going to turn into 10 multiplied by the sine of the angle. That's equal to the mass times 9.8. So, doing a little bit of math, the normal force, oops, I did a typo there. The applied force was supposed to be 20. 20 times sine 30, that's the 10. I was kind of looking ahead, is equal to 3 times 9.8. When I clean that up, 3 times 9.8 is 29.4. Flip the 10 over to the other side, I get that the normal force is 19.4. Now the horizontal component, F net equals ma. We've got one forward force, that's a component of the 20. 20 cosine the angle this time because it's adjacent to the angle. We've got 2 backward forces, friction is backwards, and that string we called ft2 is backwards. So 20 cos 30, we'll crunch that out with a calculator, that's just a number, minus the coefficient of friction, for this one was 0.1, times the normal force of 19.4, then I've got that string that I can't go any farther, is equal to 3a. Double check on a calculator, but when we get the coefficient of friction multiplied by 19.4, that's going to be a number around 2. 20 cos 30 is a number around 17 and a bit. When I crunch it out on a calculator, that works out to 15.38 minus ft2 equals 3a. I'm going to call that equation 3. Okay, going to zoom out so we can see everything all at once. There's our 3 equations. Oops. The first object led to the T1 equation. The second object, a little bit more complicated, it's got both T1 and T2 in it. Then finally this equation that we just got with just T2 in it. The cool math part of this is, since the connecting force is forward on one and backward on the other, those variables, the ft1 and the ft2, show up in one equation with a positive sign and in another equation with a negative sign. So if I write them out, I'm going to zoom out again. If I write them out there, if I go to there, equation 1 was ft1, it didn't have an ft2 in it, take away 2.94 was equal to 1a. Equation 2, I'm going to change the order. It had a negative ft1, a positive ft2, and then a negative 3.92, and that was equal to 2a. The last object, it didn't have a t1 in it. It had a negative ft2. It had a positive 15.38, and that was equal to 3a. If we write it out that way, we can see, hopefully we can see that if we add those three equations, so even though there's three equations, it's still relatively simple to solve. If we add them, the ft1s cancel out, the ft2s cancel out, we end up with the 1538, take away the 392, take away the 294, working on a calculator, I get that equals 852. On the right hand side, the 1a plus the 2a plus the 3a gives 6a. So we can quickly finish it off, flip the 6 to the other side, divide it over, and we get the acceleration is 1.42. If you follow those steps, even in more complicated ones, it should always work out. Free body diagram, F net equals ma, and then solve your system.